What's good, what's good, what's good? Okay, LeetCode, daily grind. I've been learning a lot more than I used to know, so I'm starting back over from the jump with contains duplicate. So we're gonna work in Python 3, class solution. Def contains duplicate self nums. It's a list of integers, and it's expected to return a bool. Given an integer array nums, return true if any value appears at least twice in the array, and return false if every element is distinct. So an example input would be nums equals 1, 2, 3, 1. Output true, since 1 appears twice. If we have nums 1, 2, 3, 4, output false. So init a pointer to look at every number in the array. Start at first. So pointer equals nums 0. So for num, so step through the array and check if step through the array. So for num and nums, if the number is equal to pointer, we'll start pointer equals 0. Or no, we don't need a pointer. So just step through the array, right? For num and nums, if we've seen this number before, return true. For num and nums, if num in seen list, so we'll create a list to store numbers we've seen, but see, now we're adding complexity, and I don't want to do that, but we'll do it this way, even though it's not the most efficient way. If we've seen this number before, return true. So if num in seen list, return true. Otherwise, add it to the list. Else, seen list append num. If we make it through all of that, then return false. We need to log in. Oh. Sign in with Google. It's because I have a new computer. But there's got to be a way to do it without the added space complexity. So instead of creating a list to store the numbers we've seen, what I could do is, if I look at this, step through it, so just gonna say, right, problem, I'll do space complexity O of n, because we're creating a whole other, we're allocating a whole equal list in memory. Time complexity is, we only have to look at each number once, right? We're looking at each number, but we have to compare it to something. So, well, no, we're stepping through it. We're looking, this, is it in there? No, put it in there. This, is it in there? No, put it in there. So you have to look at each of those. I think it's O of n log n. I don't know, it's time complexity. You're looking at it, you're saying, is it in there? So right, if these are my nums, starting here, right? Okay, my scene list is empty. I'm looking at this number. Is this number my scene list? No. Go add it to my scene list. Looking at this number. Is this number my scene list? So I have to check the scene list. So as far as time, it's not just dumb, and I get to it. That would be O of n. I think it's, because if I add this, every time I check in here, every time I look at one number, I have to check through my whole scene list. It's not that I have to check through these lists twice though. I think it's O of n log n. Let's find out. This method checks if there are duplicate values in a list by iterating through each element, checking if it's in a scene list. Okay, the time complexity is O of n squared. And if not, adding it to this list. Here's the analysis of this time and space complexity. Time complexity, O of n squared, for loop. Iterates through each element in the input list once, giving O of n complexity. Containment check if num in scene list. In the worst case, this check takes O of I time for each element, where I is the current size of scene list. Since scene list grows in size up to n, the length of the input list, the average case over n iterations is O of n over 2. This results in a total average time complexity of O of n times O of n over 2 equals O of n squared over 2, which simplifies to O of n squared. Space complexity O of n. Scene list. In the worst case, when there are no duplicates, this list will contain every element from the input list once, resulting in a space complexity of O of n. So the method has a time complexity of O of n squared and a space complexity of O of n. So that's not ideal, right? Definitely not ideal. Let's delete this, make it n squared. So, not good. How do we make it better? Well, instead of creating a whole separate list, we know we don't want to do this. We know we still are going to want to step through the array. So for num and nums, if we've seen this number before, return true. So if we step through it, and I look at this, I don't need to compare it to anything. Instead of looking at the numbers themselves, well, no, we gotta look at the numbers. But we look at this, we say, look at this, have I seen this before? But is there a way to do that without storing a separate place in memory? If you compare it to these, are these the same? No. Let's just see what people have said. I mean, at least I know how to do it. I just don't know what the most efficient way to do it is. Solutions. Python 3. The brute force approach compares each element with every other element in the array to check for duplicates. If any duplicates are found, it returns true. This approach is straightforward but has a time complexity of O of n squared, making it less efficient for large arrays. So sorting, hash set, time complexity, this approach O of n, O of n, O of n, O of n log n. So let's not do sorting, but well, let's see what it would be. The sorting approach sorts the array in ascending order and then checks for adjacent elements that are the same. If any duplicates are found, it returns true. Sorting helps in bringing duplicates together, simplifying the check. However, sorting has a time complexity of O of n log n. Explanation: another approach is to sort the array and then check for adjacent elements that are the same. If any duplicates are found, return true, otherwise return false. So to sort it, sort the elements in ascending order. Nums.sort n equals length of nums. This iterate through nums for I in range from 1 to length of nums. They're checking if current number is equal to the number for it. So if nums I is equal to nums I minus 1, return true. But if we make it through all of this and that never happens, return false. The time complexity of this approach is O of n log n, where n is the length of the array. Approach 3, hash set, intuition. The hash set approach uses a hash set data structure to store encountered elements. It iterates through the array, checking if an element is already in the set. If so, it returns true. Otherwise, it adds the element to the set. This approach has a time complexity of O of n. The hash set approach uses a hash set data structure to store encountered elements. It iterates through the array, checking if an element is already in the set. If so, it returns true. Otherwise, it adds the element to the set. This approach has a time complexity of O of n and provides an efficient way to check for duplicates. Explanation: a more efficient approach is to use a hash set data structure to store the encountered elements while iterating through the array. If an element is already present in the hash set, return true. Otherwise, add the element to the hash set. If the loop completes without finding any duplicates, return false. So, again, while iterating through the array, if an element is already present in the hash set, return true. Otherwise, add the element to the hash set. If the loop completes without finding any duplicates, return false. So, initialize a set to store numbers. We've seen set, iterate through numbers array. So for nums, check if the number is in our scene set. If num in scene, return true. And scene dot add num, either way, or no, otherwise really. And then at the end of our for loop, once we've iterated through every num and nums, if we made it there, then we return false. The time complexity of this approach is O of n. The issue is that the space complexity is O of n as well. So whereas this sorting approach has a time complexity of O of n log n and a space complexity of O of 1, I believe. space complexity O of 1 or O of n, depending on the sorting algorithm. Sorting num sort. The space complexity of sorting depends on the specific sorting algorithm using Python's sort method. Python's sort method, which is time sort or tim sort for a list, has a worst case space complexity of O of n. However, in practice, if the sorting is done in place and does not require additional space proportional to the input size, for example, swapping elements without using extra storage for the entire array, the space complexity could be considered O of 1 for the sorting operation itself. No additional significant space aside from the space used for sorting. This method does not use additional data structures that grow with the input size. The variable n and the loop index I are negligible in terms of space. The overall space complexity is determined by the sorting algorithm. If the sorting is considered in place with no significant additional space required, space complexity can be seen as O of 1 in terms of additional space used by the algorithm itself. However, considering the worst case scenario and the behavior of Python's sort method, which may require temporary space for operations, space complexity might be considered O of n from a conservative perspective. Okay. But anyway, hash map. The hash map approach is similar to the hash set approach, but also keeps track of the count of occurrences for each element. It uses a hash map to store the elements as keys and their counts as values. If a duplicate element is encountered, count greater than or equal to 1, it returns true. This approach provides more information than just the presence of duplicates and has a time complexity of O of n. Explanation: in this approach, we iterate through the array and store each element as a key in a hash map. The value associated with each key represents the count of occurrences of that element. If we encounter an element that already exists in the hash map with a count greater than or equal to 1, we return true, indicating that a duplicate has been found. Otherwise, we update the count of that element in the hash map. If we complete the iteration without finding any duplicates, we return false. So again, we iterate through the array. I'm going to try to do it without looking at it. So iterate through the array. Store each element as a key in a hash map. The value associated with each key represents the count of occurrences of that element. If we encounter an element that already exists in the hash map, counter element count. If we encounter, well, I'll do it like this. If we encounter an element that already exists in the hash map with a count greater than or equal to 1, return true, indicating that a duplicate has been found. Otherwise, update the count of that element in the hash map. If we complete the iteration without finding any duplicates, this would be return true. Kidding. So iterate the array for num and nums. Store each element as a key in a hash map for num count enumerate. No. I'm not sure. If we encounter an element that already exists in the hash map with a count greater than or equal to 1. So if if num so if hash map num one true. Otherwise, update the count of that element in the hash map. Else equals 1. And then we would return false if we make it through. So we iterate through the array for num and nums, store each element as a key in a hash map. So we create a hash map. So hash map num plus equals 1. If we encounter an element that already exists in the hash map with a count greater than or equal to 1, hash map num is greater than or equal to 1, return true, else hash map num plus equals 1. So we create the hash map, we iterate through it for each number. So if we have, if we have 1, 2, 3, 1, 2, 3, num, put it in the hash map with a count of 1. If hash map num is, well, I guess, couldn't I do this with how I'm doing it? So for each number, increase its count in our hash map. And then check if hash map for the given number is greater than 1. If it is, a duplicate's been found, return true. Otherwise, just move to the next number, right? Line 11 and contains duplicate. Solution, key error 1. What do you mean key error 1? For num and nums. For hash map num Python 3. So hash map equals, so call this scene. Hash map for num and nums. If num and scene num is greater than or equal to 1, return true. Scene num equals scene dot get num 0 plus 1. Otherwise, add it to our hash map and count of 1. So it seems to me here you're looking for a trade-off between time complexity and space complexity. This has a time complexity of O of n, and and the sorting has a time complexity of O of n log n, but the sorting one doesn't seem to have an extra added space complexity, whereas this one has a time complexity of O of n, but it also has a space complexity of O of n as well. Both approaches aim to solve the problem of detecting duplicates in the list, but utilize different data structures and slightly different logic. Here's a comparison of their time and space complexities. Approach 1 using a hash map, time complexity O of n, iterating through each element in the list once, results in a linear time complexity. Checking for existence in a hash map and updating it are both O of 1 operations on average, making the total time complexity O of n. Space complexity in the worst case, no duplicates, the hash map scene will store every element in the list, resulting in a space complexity of O of n. Approach 2 using a set, time complexity O of n, similar to the first approach, iterating through the list and checking for existence in a set, as well as adding elements to the set are O of 1 operations on average, thus the total time complexity is O of n. Space complexity O of n in the worst case, if there are no duplicates, the set scene will contain every unique element from the list, leading to a space complexity of O of n. Performance and comparison. Performance, both approaches have the same theoretical time and space complexities, O of n for time and O of n for space. The real world performance might slightly differ due to the overhead associated with each data structure's operations, but this difference is negligible for this problem. Readability and simplicity. Second approach using a set is more straightforward and idiomatic for this specific problem, checking for duplicates. It directly reflects the problem's intention without the unnecessary step of counting occurrences, which is not required to determine if a duplicate exists, given that both approaches have the same computational complexity. The second approach is generally preferable due to its simplicity and more direct alignment with the problem's goal. The use of a set clearly communicates the intent to track unique items and check for duplicates, making the code easier to understand and maintain. I agree. I prefer that method. So let's implement it without looking at it. So let's get off of here. So given an integer array nums, return true if any value appears at least twice in the array, and return false if every element is distinct. So create a set to hold scene numbers. Scene set equals set. Iterate through nums list for num and nums. If we can add it to our set, do so. Or sorry, it's in our set, return true. If num in scene set, return true. Otherwise, add it to our set, else scene set dot append num. Can I do that? Is that turn false? I think that's how it goes, right? Add num, not append. So if num in scene, return true. Scene dot add num. we don't need the else statement, right? Yeah. Okay. It's not going back here. What time is it? Got time for one more. Let's go to valid anagram. Given two strings, S and T, return true if T is an anagram of S and false otherwise. An anagram is a word or phrase formed by rearranging the letters of a different word or phrase, typically using all the original letters exactly once. Example 1, input S equals anagram, T equals nagaram, output true. Example 2, input S equals rat, T equals car, output false. So given two strings, S and T, return true if T is an anagram of S and false otherwise. So we need to compare the letters of S to the letters of T. So for letter in S, can I iterate through a string in? Yes, okay. Cool. So for letter in S, so I don't want to make this O(n) squared, but that's the way that's coming to top of mind for letter in S. For letter in T, so for each letter in S, you look through each letter in T. If S in T, if S for letter S in S, for letter T in T, if letter S is equal to letter T, turn true, turn false, right? That's the easy way to do it, but it's the stupid way to do it. Wrong answer. Sorry, it is definitely the very stupid way to do it. Rat, car. Oh yeah. That's not the way to do it. So if I'm being real, if I'm actually trying to do this in an intelligent way, you could sort them, right? You could store it in a list, sort the list, and then compare them. So for letter in S, list S, this for letter in S, list S dot append S letter, and for letter T, list T dot append letter. List S dot sort, list T dot sort, if list S is equal to list T, turn true, otherwise return false. accepted, but it's not the ideal solution. Python 3. Intuition. The intuition is to determine if two strings are anagrams. Compare the characters in both strings and check if they have the same characters but in a different order by tracking the count of each character. If the counts match for all characters, the strings are anagrams, otherwise they are not. Approach 1, sorting. Explanation. Sort S begin to S. So you could sort the characters in string S in ascending order. This rearranges the characters in S so they are in alphabetical order. Do the same with T. Compare the sorted strings using the equality operator. If the sorted strings are equal, it means that the original strings S and T have the same characters in the same order, indicating that they are anagrams. In this case, the function returns true. Otherwise, if the sorting strings are not equal, the function returns false, indicating that the strings are not anagrams. This code takes advantage of the fact that anagrams have the same characters, but in different orders. By sorting the characters, the code transforms the problem into a comparison of the sorted strings, simplifying the anagram check. However, it's worth noting that the approach has a time complexity of O n log n due to the sorting operation where n is the length of the strings. And actually, I'm realizing I overcomplicated it and memory allocated by doing that. I could just have done sorted. First of all, if I did s.sort, I'm pretty sure that's going to give me an error. On strings, you have to do sorted. I'm pretty sure, but I just want to check. String object has no attribute sort. Yeah, that's what I thought. So it would be sorted s equals sorted s and sorted t equals sorted t. You could just do return sorted s equal to sorted t. Approach 2 is a hash table. Explanation. Create an unordered map count to store the character frequencies. So let's see if I could just do it. Create an unordered map to store character frequencies. Key, the map represents character. The value represents frequency. So map call it char map. Iterate over each character x in string. So for char in S, for each character increment its frequency in the count map by using the count x plus plus. Well, we're not using C++. So for char in S, char map dot get s 0 plus 1. Is that how you do it? Sorry, not s. Char map dot get char 0 char map char map dot get char 0 plus 1. I think that's how you do it. Iterate over each character in T. So for char and T, char map for each character decrement its frequency in the count map by using that. So char map char equals char map dot get char 0 minus 1. Iterate over each pair x in the count map. For each pair consists of a character and its corresponding frequency. Check if any frequency x dot second is non-zero. So for I don't really know, for char and char map, if char map is greater than 0, char map is not equal to, if any frequency is non-zero, it means there is a character that appears more times in one string than the other, indicating that the strings are not anagrams. In that case, return false. So if all frequencies in the count map are 0, it means the strings S and T have the same characters and the same frequencies, making them anagrams. In this case, the function returns true. This approach counts the frequency of characters in one string and then adjusts the count by decrementing for the other string. If the strings are anagrams, the frequency of each character will cancel out, resulting in a map with all 0 frequencies. The time complexity of this solution is O of n, where n is the total number of characters in both strings. It iterates over each character once to count the frequencies and then compares the frequencies in the map, making it an efficient solution for the problem. So you'd have this count is a default distinct of integers. For char and S, char map, char plus equals 1. For char and T, char map char minus equals 1. For key or val in char map dot values, if val is not equal to 0, turn false. If we make it through all of that, turn true. Approach 3, hash table using an array. So you have to create another one. Should I even bother learning this? Let's figure out. Both solutions aim to determine if two strings S and T are anagrams of each other, i.e. they contain the same characters in any order but not necessarily contiguous. The solutions use different data structures to count character frequencies. Let's compare them based on efficiency, scalability, and readability. Solution 1 using default dict. The solution uses a default dict from Python's collections module to dynamically create dictionary keys for characters as they are encountered. Its efficiency lies in the fact that it can handle any Unicode character, making it versatile for strings with diverse character sets. Scalability, it scales well with the string's length and character diversity, making it suitable for inputs with a wide range of characters beyond just lowercase alphabetic characters. Readability, this code is straightforward and easy to understand, utilizing Python's default dict to manage character counts, using a list for for alphabet characters. Efficiency: the solution is optimized for strings containing only lowercase English letters A to Z. It uses a list of 26 elements where each element's index corresponds to a letter in the alphabet, and its value represents the frequency of that letter. This can be slightly more efficient than the dictionary approach for cases where the character set is known and limited, because it avoids the overhead of hashing keys and handling collisions in a dictionary. Scalability: it's less scalable in terms of character diversity, since it assumes the input will only contain lowercase alphabetic characters. For inputs outside this range, the solution would now work correctly without modification. Readability: while still clear, requires understanding that the indices of the list correspond to letters in the alphabet, which adds a slight cognitive load compared to the direct character handling in the first solution. Preference and conclusion: the first solution is preferable when working with strings that may contain a wide variety of characters, including uppercase letters, numbers, symbols, and non-English characters. Its use of default dict makes it more versatile and applicable to a broader range of inputs. The second solution is preferable if you are certain the inputs will all be limited to lowercase English letters. It might offer better performance due to the fixed size and direct access nature of the list using counting. Okay, so what are the time and space complexity each? So time complexity O of n for this first solution. Space complexity O of u. The space complexity is determined by the number of unique characters in S&T. In the worst case, where all characters are unique, the space required for the dictionary will be O of u, where u is the number of unique characters across both S and T. And the time complexity of the other one is O of n. Space complexity is O of 1. The solution uses a fixed size list of 26 integers corresponding to the 26 lowercase English letters, regardless of the input size. The space required for this list does not change, making the space complexity O of n. So comparison: both solutions have a time complexity of O of n. The first solution has space complexity O of u, which can vary depending on the number of unique characters. The second solution has a constant space complexity O of 1, making it more space efficient for inputs limited to lowercase English letters. If you know that the input strings will only contain lowercase English letters, solution 2 is more space efficient with a constant space complexity. For inputs that could include a broader range of characters, solution 1 is more versatile. Interesting. Let me, how much time? I don't really have time, but we look into default dict. Dictionary in Python is an unordered collection of data values that are used to store data values like a map. Unlike other data types that hold only single values as an element, the dictionary holds key value pair. In dictionary, the key must be unique and immutable. This means that a Python tuple can be a key, whereas a Python list cannot. A dictionary can be created by placing a sequence of elements within curly braces separated by a comma. So dict equals 1, geeks, comma 2, 4, comma 3, geeks, print dictionary, print dict 1, would print geeks. Default dict is a container like dictionaries present in the module collections. Default dict is a subclass of the dictionary class that returns a dictionary-like object. The functionality of both dictionaries and default dict are almost the same, except for the fact that default dict never raises a key error. It provides a default value for the key that does not exist. I see. Okay, cool. Well, I just wanted to get a little bit of practice in, but I don't have much time today. Got a long way to